In this lesson, we're going to add some more exponent rules to our basic knowledge. We're going to look at rational exponents, that is, exponents that involve fractions. Before we do that, we're going to quickly review the previous ones, just so we are handy with those, because they're going to come into play also. Okay, rules, remember, bedmass if you see adding or subtracting, and really bedmass, even though you're dealing with exponents, should still apply to everything else. If you can do things in brackets, we would do that first. If we have exponents, two exponents, you do that next. Then you deal with your division and multiplication idea. So I want to simplify these, and I want to make my answers have positive exponents only. So we may have to deal with reciprocals. So the first one, I see a power to a power, an exponent to an exponent, basically. So I need to do that first. I'm going to multiply to get that. When my bases are multiplying, I can add my exponents. So 7 plus negative 6 is 9 to the 1. It's a positive exponent, so I'm done. Next one, bases are the same when they're multiplying, so we can add. I see negative exponent, we don't like that, so we bring it to the bottom, make sure we have something on the top, it's got to be the number 1. Try the next one, I see bases that are dividing. When I divide, I'm supposed to subtract my exponents. So I'm going to take 2m plus 3n, and I'm going to subtract m minus n, which, if we think of this as algebra now, means I can get rid of my brackets by expanding them. And if I collect those like terms, we'll get m plus 4n. And the last one, okay, bedmass rule says I should do things inside brackets first. So I'll leave this piece alone. Inside the brackets, I'm dividing, so I'm going to subtract those two exponents. So 2 minus negative 6 will give me an 8. And my bases are multiplying now, so I can add, I get 2 to the 7. Okay, so those are the rules we went through yesterday with integers. So occasionally we have negatives, we've got to deal with those. We're going to add some stuff to our exponent rules. So a rational exponent. A rational exponent means anything as a fraction. For example, 1 over n. We call this the nth root. And what it really means is we have a root sign now. And whatever's on the bottom goes in front of that root. Now, it's not the same as saying n square root x. What we're really saying here is the nth root of x. So the x is here, and the n's that little number outside. Okay? The number at the left of the root sign, the bottom of the fraction, is called our index number. So for example, if you have the number 3, look at that, x to the 1/3, we would call this the third root of x. If it was x to the 1/4, it would be the fourth root of x. 1/5, the fifth root of x, and so on and so on and so on. The one special case is if you see a 2. X to the half is just the square root of x. We don't usually put the 2 in here. That means square root. Okay, so if we ever come across a square root, we can write it as a half. If we see a half, we can write it as a square root. Okay. The idea of this nth root is kind of the opposite of exponent. Instead of making things bigger, it's actually going to make things smaller. For example, a cube root, so cube root 8 to the 1/3, means find a number that when multiplied by itself 3 times, creates 8. And what number times itself 3 times makes 8? Well, we know that 2 to the 3, 2 times 2 times 2 is 8. So 8 to the 1/3 means I need 3 2's. Okay? That's kind of the idea here, that we're going to make fractional exponents make our base smaller. So we're going to try some of these. I want to evaluate. I need to think to myself, 16 to the 1/2. What does that mean? That means the square root of 16. We don't put the 2 there, though we know it's actually there, okay? Square root of 16, that's 4. 25 to the half. That means the square root of 25. That's a 5. 27 to the 1/3. Well, here's where our roots come in handy. Cube root of 27. What number times itself 3 times makes 27? And 3 times 3 times 3 makes 27. So the cube root of 27 is 3. Now, if you can't think of it, there is a button on your calculator. It usually looks like this. And what you type in is you type in 3, press that button, and 27, and it should come out to 3, the cube root of 27. Okay, we'll try the next one. Now, I noticed a little problem in this one. I see negative exponents. Before we do rational exponents, we want to get rid of those negatives. We do it the same way we did previously. So I flip my base and make my exponent a positive. Now notice I didn't flip the exponent. That's a common mistake. The exponent's sign is the only thing that's going to change. So what we need to think to ourselves is 1 over the 6th root of 64. What number times itself 6 times makes 64? And again, if you can't think of it, we go back to this button idea here. We say, okay, the 6th root of 64 comes out to, hopefully you get 2. Okay, we'll try some more. 125 to the negative 1/3. Oh, negative exponent. Flip it. Okay, my exponent becomes positive, which means I want the cube root of 125. What number times itself 3 times makes 125? That would be a 5. Don't forget the one on the top of the fraction. It's kind of important. All right, next one. Cube root of negative 25. What number times itself makes negative 125? Oh, a negative 5 times a negative 5 times a negative 5 does it. So we can take cube roots of negatives, even though we couldn't take square roots of negatives. And the reason why is we have an odd number now. Last one, 4th root of negative 16. 4th root of negative 16. What number times itself 4 times makes negative 16? This one is not possible. Right? Whenever I want to take a 4th root, something times itself 4 times, there's no way I can end up with a negative number. Because these 4 things inside the brackets all have to be the same, they can't all be negatives because 4 negatives makes a positive. So kind of a little trick here. If your number is an even number on the bottom of the root sign there, negative roots aren't possible. In the previous one, we had an odd number. Well, a negative root is possible because you end up with 3 negatives, and 3 negatives make a negative. But if it's an even number, can't do it. Okay, kind of a little trick. Okay, let's add a little piece. What happens if the number on top of the fraction in the exponent isn't 1? Right, well, we can still do the same thing, and we can think of it in 2 different ways. Okay, we can think of it as a nth root to a power of a whole number, or the nth root of your base to the whole number. Now my preference is we do the first one. Figure out the nth root first, and then apply your exponent. Because it makes your number smaller, and then afterwards bigger. But you could equally do it by doing the exponent first, and then the nth root. Works totally the same way. And we'll try some examples to show you how that works. Okay. Really, this situation is like a power to a power. It's a to the 1 over n to the power of m, which, okay, if I multiply these 2 things together, it gives me m over n. That's really what we're doing. We're breaking into 2 pieces. So we try this first one here, 32 to the 3/5. I'm going to do it as 32 to the 1/5 to the power of 3. Okay, what is that going to look like? Well, it's going to be the 5th root of 32, all to the power of 2. Oh, sorry, to the power of 3. What number times itself 5 times makes 32? 2 does. 2 to the 3, that comes out to 8. If you didn't want to do it that way, you could have just as equally, let's move these other questions out of the way for a second here, okay? You could have done 32 to the 3, all to the power of 1/5. But I hope you see the problem here. 32 to the 3 is going to create a huge number. It's not wrong to do it, and it's going to work out totally the same answer. It's just we're going to have these really big numbers to have to deal with. I don't want to write big numbers down. So I get 32,768 to the 1/5. Or in other words, the fifth root of 32,768 comes out to 8. It's the same answer. It's just bigger numbers, right? Small numbers are easy. You can probably do those in our head just as fast as we can do them with the calculator when we do the big numbers. All right, we'll try some more. Let's move these down here so we have some space. 27 to the 4 thirds. That means 27 to the third, all of the 4. Or in other words, cube root of 27, which gives me 3 to the 4, which gives us 81. Hit them quick. Okay, small numbers, can do those ones in our head. Okay, letter C, I see negative exponent. I've got to flip my base. My base is the 16. The exponent, same numbers, just make it a positive, which will give us 1 over 16 to the half to the 3. Okay, which I can simplify that. That just means 1 over root 16 to the 3. Or in other words, 1 over 4 to the 3, which is 1 over 64. Okay, deal with the negative exponents first, then you don't have to worry about them anymore. All right, that's still 2 here, D and E. Okay, negative 8 to the 2 thirds, so negative 8 cubed squared. Okay? Instead of writing it as the 2 separate exponents anymore, let's just write it real quick. The cube root of negative 8, I can do that because it's an odd number. I'll give you negative 2 squared, comes out to 4. And E, I see a fraction to a negative. If I flip my base, that means I flip the whole fraction. Make sure it's the base we're flipping. 4 over 9 to the power of my exponent. Exponent becomes positive. Don't change the exponent otherwise. Don't flip the exponent, just change its sign. How are we going to apply this 5 halves? Top and bottom. So if you want to, we can think of it as 4 to the 5 halves over 9 to the 5 halves. What does that really mean? The square root of 4 to the power of 5 to the square root of 9 to the power of 5, which gives us on top 2 to the 5, on bottom 3 to the 5, or 32 over 243. Okay, so lots of parts of pieces and lots of steps. You don't necessarily have to show every step. We're doing it now so we can learn where they're coming from, okay? Okay, I want to simplify where possible and then evaluate. I want to write my answers in rational form. We've talked about rational numbers before. Those are root numbers, right? Now our roots might have little nth values in front of them, okay, index numbers. So let's give this a try. 81 to the 1/2. I can simplify that. That means the square root of 81. Cube root of 8, I can calculate that. That means 2. 32 to the 4/5. I can simplify that. I need to take the fifth root of 32 and put it to the 4. And the 3/4, 16 to the 3/4 means the fourth root of 16 cubed. Square root of 81 I can evaluate. That's 9. 2 is 2. Fifth root of 32 makes 2 to the 4. Fourth root of 16 makes 2 to the 3. Again, I can calculate. 9 plus 2 is 11. Minus 16 plus 8. Or in other words, I can get 3. So the big mess of integers and exponents and all those other things comes out to a nice whole number. Okay, we try B. I can apply exponent rules. On the top, I see bases are the same and they're multiplying. So I can add those exponents. That'll give me 8 to the positive 0.5. On the bottom, I see a power to a power. I should multiply those exponents. 6 times negative 0.25. That gets me a negative. That gives me a negative 1.5. I've got bases that are the same and they're dividing. I can subtract those things. That'll give me 8 to the 2. Oh, that's easy enough. That's 64. Okay. Don't deal with the negative signs or the fractions or the decimals until you've tried simplifying things. Hey, if you can apply exponent rules to make it easier, let's try and do that first. Okay, last one. What do I see here? I see the fourth root of 16 over 81 to the negative 1. What should we do first? Well, we talked about root signs acting like brackets. So I should do the stuff inside the bracket first. What is 16 over 81 to the negative 1? Well, I see a fraction to a negative. I flip my fraction. Make my exponent positive. Now, do I really need the 1 there? No, because anything to the power of 1 is just 1. Sorry, anything to the power of 1 is just itself. So I don't really need the 1 there. I don't need it. And I can just write this as the fourth root of 81 over 16. Well, what does the fourth root have to apply to? It's got to apply to both the top and the bottom. What's the fourth root of 81? 3. Fourth root of 16? 2. And we've simplified and then evaluated. Yeah, that's the end of our rational exponents. You notice we've combined some of those with our previous exponent rules too, so we kind of need to know both. Okay. You can use your calculator as necessary if you're not sure about your nth root. Use your nth root button, but it's pretty easy to do some of the smaller ones in your head, and it'll probably be a lot quicker.